So hi everyone. Now we will go through the second place solution of CAFA competition. So here is the agenda, and we're going step by step. But first, let me introduce me and my team. Our team name is U900, and my name is Anton Vafrushev. I have about 8 years Kaggle experience. Besides that, I have education in applied math for the economics. And actually, my current experience is more than 10 years of data science and R&D in banking. And one of my research areas is research on applying gradient boosting decision trees to kind of multi-output problems, including extreme multi-label tasks. So it motivates me to enter this competition, like to evaluate some of my approaches and also my open source libraries that we developed during our work. Now I give word to my teammates to introduce themselves.
Hi everyone, I'm Sergey Pironov. I've joined Kaggle many years ago, but my active experience is only 8 years. I working for a long time in the mass spectrometry field with some proteomic data, and this is the main reason that I joined this competition because it reminds me something about this work. I've trained a lot of networks for this competition, but it was not so successful as I want. That's all.
Hello, my name is Alexander Chervov. So my education is in mathematics. Then I worked in industry and some data analysis and data science. And last 4 years, I'm working in bioinformatics and data science in the Institute Curie in Paris. And so I'm quite interested in this competition. Hopefully, I can apply these methods which we developed to some of our problems, in particular, some kindness and substrate interaction. So hopefully we can predict some interaction between kindness and substrates better with these methods. And that is one of my motivations to enter the competition. In general, I have maybe about 5 years of Kaggle experience, but maybe active is only 1 or 2 years. But I think Kaggle is a great platform. I'm using it as a kind of not only for competition, but for my everyday work. I'm trying to do all my projects on Kaggle instead of Google Colab, for example, or local Jupyter notebook. Okay, probably that's all. Thank you very much.
Thank you, guys. Okay, and here is a brief summary of our approach. You can see it's like a very typical for Kaggle. There are some feature extraction part, some basics model, some stacking part, and post-processing part. So every part is quite typical. But here we have an additional part is working and parsing the external data, which we take from FTP source with Go annotations. But actually, it's very similar to any kind of competition. Let's just go step by step to explore each part. And first, let's start with features and base models. As base model features, we use 2 types. First is like protein embeddings, like sequence embeddings. Here we used 3 types of protein models. First one is T5. It works extremely good, and it's used in all kinds of our models. The second one is perform a little bit less. It's ESM small, and this embedding is used in some of our models. And the third one is ANC large. We just tried this embedding, but we rejected it because it didn't boost performance of any model. Okay, and the second part of features is taxon features. It's a simple one-hot encoding. So we just extract about 35 taxons that are good enough represented in both train and test sets. So it has enough frequency in train set to train something, and it also it exists in test set also, so it makes sense to train something. So it's about only 35, and the other taxons we joined to the one single group we called other. Just 2 types of features, and all our models, base models, are based on this. The second thing I want to tell about is validation. We had a lot of experiments on developing like smart validation strategies, but we didn't succeed. We tried to split faults in that way that faults will not look like each other. So different proteins, different types of proteins in different faults, but all the models with smart validation strategies performs worse on the public leaderboard. That's why the best we can do is just do like a group K fault by unique sequence. So different protein IDs with the same sequence cannot be in different faults. Actually, it's very typical. It's like a normal 5-fold CV because there are not too many duplicated sequences. And the second part, second validation strategy is used for our stacking model. We will speak about it few slides later, but our stacking model is built on the full train set. So we used a part of the test set to make a validation, and we use Go annotations to label some leakage part. Like everybody knows that there is a small set of protein term pairs that overlaps between public leaderboard and the test set and the Go annotation database. So we used about this, maybe about 500 protein term pairs to validate the stacking model. Let's go to check what we built on the top of it. Okay, the best performance model was from gradient boosting family, and what's the most interesting part about it? That is my own implementation of gradient boosting called PyBoost. It's actually open source, and you can check it on the GitHub. It's also available via PyPy. And what the most interesting part about the PyBoost, that it was developed especially to handle with extreme multi-output tasks. Here we build a special algorithm to speed up a multi-output training. So for example, when you train multi-label for the hundreds or 1,000 labels or classes, speed up compared to the state-of-art implementations like XGBoost or CatBoost, it could be very significant. It could be tens of times or maybe hundreds of times. So here you can see the comparison of different gradient boostings in terms of time to train 100 extra iterations, 100 extra trees. So you can see that time of our boosting is much less compared to XGBoost or CatBoost if we speak about hundreds of classes. You can read about our approach, how to speed up multi-label computations on our new RIPS paper. And here, all we care about is that this is a gradient boosting. It can do multi-output very fast, and that's enough for us. So we built two types of gradient boosting. First type is built on top of T5 plus taxon. The second built on top of T5 plus ESM plus taxon. All the models were trained on the multi-label tasks, and we just, as labels, we took 4,500 outputs, and PyBoost takes about maybe 2 or 3 hours to train a single fault. And this is like a top performed model from our base models. The second type of model is a simple logistic regression. It's trained on top of T5 plus taxon features. It's actually performed much worse than gradient boosting, but since it's a very simple model, it could be built for much more labels, and we trained it for 13,500 labels. And the last part is neural networks model. We take one of the publicly available notebooks which train neural networks and slightly modify it. Modifications are quite simple. We just do a proper parameter tuning. and we perform a multi-start. So we just perform multiple runs with different random states and then average the results. Features in this case are T5 plus ESM embeddings without taxon features, and it's trained on the 2000 outputs. So we had actually 3 types of base models, but there is one small modification. Everything we discussed before was quite simple, but the next it's a little bit brainwashing thing. It's like an alternative modeling approach. Instead of modeling the classic multi-label task, we perform modeling of conditional probabilities. How did we came to this approach? All these models before that we trained didn't use obograph at all. So of course we agreed at the beginning of the competition that finding a proper way to use an obograph is the key to win in this competition. So actually, from the beginning of the competition, we were trying to find an approach how to utilize the obograph. And here, this is the first approach that we came with. Here you can see like an example of a graph. First, you can think you should know about this graph. This is a not real graph. Here are just random go IDs. And actually, this graph cannot exist. But it represents how we look at the graph at the beginning of the competition with our small prior knowledge. What we decide to do? We replace the classic multi-label labeling when, for example, if we have a protein term pair in labeling, we mark it as 1. If we don't have protein term pair in targets, we mark as 0. It's simple. We create a new labeling where targets could be 1, 0, or none. In what case targets going to be none? For example, if there is one term, for that term, all the parents are 0. Then we mark the term none. If at least one parent is 1, we can mark the term as 1 or as 0. So what does it mean? We're trying to estimate the conditional probability of term in case when at least of its parent exists. Why is it wrong? It's wrong because the assumptions are wrong by design. For example, we have Go6 labeled as 1. It's a child of Go3 labeled as 0. But since we have propagation rules while building a target, I mean CAFA 5 target, there is a propagation made. So if Go6 is 1, Go3 will be also 1 because of the propagation rules. That's why I marked it red to show that it's not real. It's just our view on the moment of discovering the approach. But okay, we assume that it could be 1 or 0. Parent could be 1 or 0. The other assumption is that the probabilities of parent terms are independent. It's also wrong just because of, again, propagation rules. So they are going to be all 1s. So they are not independent. But if we assume these 2 points, we could convert the model probability of term, conditional probability, to the raw probability using this formula. What's good about this formula? Actually, it's recursive. So for example, imagine you computing raw probability of term for some term. You use conditional probability of term by multiplying this thing. And here, this is a parent's probabilities of term. But parents' probabilities are actually included grandparents' probabilities calculated already. And so when you calculate term probability, all its relatives already included in this formula. So you cannot ignore the probability of parents while computing the probability of child. Even though this approach is wrong by design, it works. so it performs better on both CV and leaderboard. Not too much, but significant, maybe 1% of CAFA score. What's very good about this approach, it leads to a very different model compared to the default multi-label approach. So finally, what did we have? We, for gradient boosting and for logistic regression, we trained two types of models. One type is a classic multi-label. Second type is a conditional probabilities approach. Combining it all together boosts score a lot because models are very different. But just for neural networks, we keep it as is, like a classic multi-label approach. Okay, now we need to collect it all together. And here we go to the stacking phase. We also utilized graph at the stacking. And here is a quite simple approach. If we think about the protein at the graph and think about the term like a node, we can take an graph like an adjacency matrix and say, let's train a graph convolution network for a node classification tasks. It's a very common approach, and it's very easy to implement. So in this approach, we can use base models predictions as a node features. We can also add some trained node embedding. And here we add some Go annotations. What about Go annotations? There is a source. It was available on the forums, and a lot of people using this source to get Go annotations. There were also some public data sets. And we use this data source to collect the latest Go labeling. But what is good about this? It contains not only the 1 or 0 label, they also collect evidence codes. So for each Go annotations, we can say if it is experimental, that we need actually to predict, or if it's electronic. So we can use electronic as the features, but we can use experimental like extra validation or some leakage knowledge that we can add to the data to make submissions. So what did we do? We just add one feature, 0 or it's a binary 0 or 1. If we can meet a protein term pair in Go and electronic labels. According to our analysis, only 30% of electronic labels finally become experimentally found in this data set. So, for example, a lot of public kernels just take all the electronic labeling and add it to the submissions. But use it as a feature is much more efficient. And we did it on the stacking phase. The last thing, last few things I should mention here. We trained that stacking model using only T5 based models. But as I told you before, we trained both T5 plus ESM models. Because of one mistake, we just shuffle the model's ID and get a good score. That's why we understood that models are not different from each other too much, and it could be like a kind of augmentation. Let's shuffle some model IDs and make multiple predictions and then average, and probably it's going to increase the score. And it happens. Yeah, this trick increased score a little bit, and we just use it for the final submission. The last thing I should mention about the stacking part is about the metric. I spent a lot of time trying to understand better how metric is computed. And as far as I understood, we evaluated only on the protein ontology pairs that are experimentally formed. So you can imagine this situation. For example, we predict 3 terms for a protein from a biological process. Imagine CAFA team mark only one from it as experimentally found. So what we get? We will get some value from the marked by CAFA team, and we will get some penalty for 2 that were not marked. But for example, if CAFA team found 0 of our 3 biological process, we will just not get any penalty. So if we have some overlap, we will get penalty. If we have 0 overlap, we have 0 penalty. I don't know if it makes sense from a point of real life, but here how is the metric work. So the right way to fit a final stacker model is excluding rows that consist of only zeros. Yeah, the stacker model trains independently for each ontology. So there are 3 stackers for biological process, molecular functions, and cellular components. And if some protein doesn't have an ontology, you should just drop it from the sample, and it's going to be the right way. Here are the details about the model, how it works generally. We had some model predictions. Each model predictions is transformed to 4 features. What are the features? First feature is a prior flag. On the second phase, we assume that all the models have the predictions for all the terms. If, for example, one model wasn't trained on term, we just replace it with a prior, and we mark a prior flag as 1 in that case. So the stacker model knows that this is actually a prior prediction, not a model prediction. The second is just a raw model output. So for conditional model, it's going to be conditional output. For the raw model, it's going to be raw output. And the 2 second features are 2 propagation features. The first propagation feature is like a transforming conditional probabilities to the raw probabilities, the same formula I described before on the stage of alternative modeling. The second is like an alternative propagation rule. It came from another assumptions. Actually, as I told you before, this formula works, but it is wrong. So we just create another formula. It's also wrong, but it's also somehow works. What's the main point? Both these features are utilizing the Elba graph. This is important for us. So each model is converted to 4 features. So we have 20 features came from model predictions. We have single feature from Go labeling, and we have a term ID embedding of length 8. So each protein term pair is represented by 29 features. We'll make like a concatenation, some normalization, and get like a general joint term embedding. Then it goes through graph convolution layers multiple times. But there are 3 separate layers. First layer traverse graph forward from parents to children. Second one independently traverse it backward from children to parents. And the third one just traverse both sides, and it's like bidirectional. And then all the outputs of these graph convolutions are concatenated and just go to the classifier. That's how it works. Okay. One of the last parts is the post-processing. What's the problem of protein term prediction? Actually, as I told you before, we have this slide. This situation is not normal, because if a child is 1, parent's gonna be 1. So consistent model should never predict the probability for child higher than probability for parents. But actually, only conditional type models cares about it. For example, our stacker model is a simple multi-label, and it doesn't care about it. So you can think that a stacker model can output inconsistent prediction. For example, probability for child more than probability for parents. So we can manually fix the situation. Again, we use OBOGraph for this. First time we traverse the graph from parents to children. and replace each probability for children like weighted average of minimum of parent probabilities and term probability. Then we independently traverse graph backward, and then we compute probability for term like maximum from child probabilities and term probability, and then we just average minimum propagation and maximum propagation steps. So here's like an explanation on one example how it works. This step actually boosts scores very little, but I hope it makes like models more stable. So finally, how did we build our solution from the when modeling part finish? So we have predictions from stacking. What did we do? We perform this post-processing. It's quite fast. It takes about 5 minutes. Then we add some publicly available data sets. For example, it was data sets by MT. It contains 37 proteins. We added to the submission file. Then it was another data set that contains electronic labeling. Actually, the both data sets are just the same source that we used, but from the previous timestamps. So when the competition finished, we were trying to reproduce these data sets from the FTP source, and we found that actually, if we do like we do, but with another time slice, we get the empty data sets. So we just take a difference and reproduce what we had with the public ones. And then we just compute an average probability as a final submission. Then just drop all the probabilities with less than some cutoff, 1%, and select top 100 if there are more than 500. Okay, and here is some ablation study. We started with PyBoost model, and single PyBoost model gets about 51 score. Then adding the taxons to this model gets about 53, and then blend of all the ML models get 55. Then we add some leakage to get 57. Then we join public neural network and get 59. And when we switch from a blending setup to the stacking setup and post-processing, we get around 62. So it's our final submission. Speaking about a simple model, we believe that we should not use some kind of simple model here, because there is no need to make a fast and efficient inference for this kind of tasks. And each single model score is much less. But actually, after I made these slides, I think that there is one thing that we can reject for the simple model. For example, this test time augmentation takes about maybe 2 hours, but a single model submission takes about 1 hour. But difference is quite difference is not too big. So to simplify, you can just reject the TTAs from model, but you should use all the models anyway. What you should not use, of course, you should not use some leakage data that we add to the submission. So steps 2 to 4 on the building and submissions are just for competition. So it's not useful for real life. In real life, your solution will end with a post-processing stage. Speaking about train time, here I provide detailed train time for all the steps of pipeline. If you have just single GPU, it takes about 4.5 days to reproduce all. But I suppose the optimal timing is gonna be 2 days with using 3 GPUs. In this setup, all 3 GPUs is gonna be utilized for all the time, so it's maximum efficiency, and it takes about 2 days. If you take the model only for inference, it takes about 3 hours with test time augmentation, and maybe about 1 hour without test time augmentation. Okay, that was our presentation. That's all I wanted to say. And we made our solution publicly available on the GitHub. So if you have any questions, I can answer.